Sex-linked genes are genes that appear on the sex chromosomes, and thus their patterns of expression are controlled in part by the sex of the individual. In humans, 22 pairs of chromosomes are autosomal, or non-sex chromosomes, and the 23rd pair are referred to as the sex chromosomes. Females have 2 X chromosomes for their sex chromosomes, while males have an X and a Y chromosome as their 23rd pair. Now, as you can see from this picture over here, the X chromosome is much larger than the Y chromosome. And in fact, the Y chromosome is only a portion of the genes, has only a portion of the genes that the X chromosome does, around 100 genes on the Y chromosome, and they control many of the male sex characteristics. The X chromosome has around 1100 genes. So the important point here is that the genes on the X chromosome are not on the Y chromosome. Thus, males can only have one allele for every gene that appears on the X chromosome. They simply don't have a homologous chromosome with the same set of genes on it like the females do. So as you can see here, we're just showing that, for instance, if a recessive allele for a gene on the X chromosome is present in the male, well, there is no other allele on the other chromosome that could possibly be dominant to mask it, and therefore males can't be homozygous or heterozygous for any of the genes that appear on the X-linked chromosome, because again, they have only one allele for every gene. Color blindness is an excellent example of a sex-linked trait, and the gene for color blindness occurs on the X chromosome. Now, colorblind individuals would have a hard time seeing the number 74 in this image, and there are different ways of being colorblind as well, different variations of it, and some might see a different number here or no number whatsoever. Now we're going to use the letters F to denote the color vision allele. So full color vision would be a capital F, a dominant trait. Colorblind is a recessive trait, using the lowercase f. Now, a colorblind male, we would have to designate, first of all, that this is a male and use the X and Y symbols. And to denote that the male is colorblind, then we would use the recessive allele as a superscript on that X chromosome. And of course, there is no allele on the Y chromosome, and thus we don't put one there in the symbolism. So you can see this one large X chromosome, which is necessarily maternal, and the smaller Y chromosome from the individual's father, without any gene at all. Now, a colorblind female would have to be homozygous recessive, because again, she has 2 homologous X chromosomes with this gene. So a full color vision male would have the dominant allele on his X chromosome, and again the Y chromosome simply would not have any gene on it whatsoever, and thus that's how we would represent it in the symbolism here. Now, a full color vision female, of course, follows the generic dominant recessive system. She could be homozygous dominant for the colorblind allele, the capital F on both homologous chromosomes, or she could be heterozygous for this trait. Either of these situations results in a full color vision female. So I want you to pause the video in a moment after I pose a couple of questions related to this. Cross a colorblind male with a female carrier. Now, carrier is just a word we use for a heterozygous person, carrying the trait but not expressing it. Use the capital and lowercase f to denote full color vision and color blindness respectively. And after you do the cross, answer the following questions. What is the probability that the child will be colorblind after a cross between these two individuals? And then what is the probability that they will have a colorblind daughter? So go ahead and pause the video now and work this out. Okay, so the first thing you want to do in any sex-linked cross is denote the father and the mother. So place the correct identity of the chromosomes on the Punnett square, the X and Y for the father and the X for the mother. And then go ahead and fill out the Punnett square using the X's and the Y's. So here we see 2 of the outcomes are girls, 2 of the outcomes are boys, and thus that's in line with what we expect in the world. 50% daughters, 50% boys, 50% chances of both. And then we can go ahead and fill in the alleles. So again, we wanted to cross a colorblind male. Now he is just going to receive that recessive allele on the X chromosome, nothing on the Y, because this gene does not exist on the Y chromosome. It is only on the X. And the mother was a carrier. She's heterozygous, so we see both of those alleles, one on one X chromosome and one on the other. And then we'll continue to fill out the Punnett square as appropriate, just putting that single allele on the X chromosome for the males. So this is what you should have come up with. And thus we see that the chance of a colorblind child is 50%. Down on the lower region we see 2 colorblind outcomes. And the chance of a colorblind daughter now, out of all the possibilities, is 25%. Only one of these outcomes resulted in a colorblind daughter. Okay, and then I want you to answer the following question. Again, pause the video and think about this for a moment. Why is it possible for a man and a woman who both have full color vision to have a colorblind son, but it's impossible for them to have a colorblind daughter? Okay, so take a minute to think about this. Okay, the answer is all about the father here. If the father has normal color vision, he will pass on his X chromosome to his daughters, and his daughters will get the dominant allele for normal color vision, and thus regardless of the other allele, if it's recessive or not, those daughters are going to have normal color vision, so it's impossible for them to be colorblind. Now if we go ahead and continue with the mother, if she is normal color vision, normal full color vision, then she would have the dominant allele present, and thus she'd pass it on in her gametes, and we see that this would result in a homozygous dominant daughter and a dominant male, or a full color vision male. However, she could be a heterozygote, and if that was the case, then that would result in a heterozygous full color vision daughter. However, this would result in a colorblind son. And thus that's how it's possible to have a colorblind son but not a colorblind daughter from the mating of these 2 individuals. Males only get their X chromosome from their mother. They have an X and they have a Y. They had necessarily got their Y from their father, so they could only get their X chromosome from their mother. And that's why males in the population tend to have an increased chance of color blindness, because again, they express whatever allele they inherit. So if their mother had the colorblind allele, there's a good chance that they themselves will be colorblind.